Hello everyone, my name is Han Leong, a Year 4 student from the School of Computer Science and Engineering, and today I will be presenting my FYP, which is the stock prediction on Tesla using sentiment analysis on stock tweets. My supervisor is Associate Prof. Yo, and my examiner is Prof. Guan. Here is the agenda for my presentation. I will be introducing to you guys to my project, followed up by how I implemented my sentiment analysis and stock prediction models. Next, I will discuss my results and I will conclude my project after that. First, let's take a look at this diagram. This is Tesla's stock price chart from June to November. From the chart alone, just by recognizing the pattern and noticing the trend of Tesla's stock price, one would imagine the price of Tesla stocks to continue to rise. However, if I were to provide more information regarding Tesla stocks, to be more specific, tweets about Tesla stocks, let's see how this changes one's predictions. Here are some screenshots of tweets about Tesla made by the CEO of Tesla, Elon Musk, as well as some of the netizens' replies. Here, Elon Musk states that he will be selling 10% of his stocks, and some of the replies to his post include stating that the Tesla stock is going to end its amazing run, and the Tesla stock since that post is going to drop. So, after seeing these screenshots, I would imagine some of you to change your prediction such that Tesla stock price is going to drop after this instead. In fact, Tesla stock price did drop after this, decreasing by almost 15% on the 9th of November. Hence, the objective of this project is to determine the usefulness of social media sentiments on stock prediction. To achieve this objective, I will be comparing the performance of neural network models that are trained on just the stock price only versus another model that is trained on both stock price and sentiment analysis. For the scope of the project, I'll be focusing on Tesla stocks. The rationale for choosing Tesla is the erratic nature of Tesla's stock price in recent years. As you can see, in the past few months, there have been huge spikes and random drops in the stock price. This dataset allows us to provide a clearer performance between the models that were trained on external features such as social media sentiment, since these random ups and downs in the stock price will provide to be challenging for models that only train on the stock's historical data. For the sentiment analysis aspect, I will be focusing on harnessing tweets from stock tweets. The reason for choosing this over conventional social media platforms such as Twitter is the additional features that stock tweets provide. As you can see from the circled parts, stock tweets allow users to include a bullish or bearish tag to indicate their sentiment in that post. This can be used as target labels when training the model, which saves us time from manually analyzing each tweet and labeling the sentiment on our own. Furthermore, users are able to tag which company stocks they are referring to when making that post, allowing us to specifically scrape for tweets that mention about Tesla stocks only. So after introducing to you about my project, let's take a look at the overall pipeline of how I intend to implement my stock prediction model. Firstly, I will gather data from stock tweets and pass them into a sentiment analysis model to perform sentiment analysis on social media posts. Next, I will gather historical data about Tesla stocks and combine it with sentiment features predicted by the sentiment analysis model. These combined data will be fed to the stock prediction model, and the performance of the model's stock prediction on Tesla will be analyzed. Now, let's take a look at my implementation of the sentiment analysis model. In general, sentiment analysis usually involves natural language problems. The paragraphs of text can be viewed as sequences of words that come one after another. Hence, we can use recurrent networks to model this problem. However, recurrent neural networks suffer from the problem of vanishing gradients. When the network is learning during the training phase, if the gradient that is backpropagated is a fraction, when it gets passed back through multiple layers, the gradient gets smaller and smaller, eventually becoming too insignificant, causing the layers at the start to not learn anything at all. Hence, I turn to another more advanced recurrent network, which is long short-term memory, or LSTM model in short. The cells in the LSTM model are more complex and includes forget and input gates. These allow each cell to retain a certain amount of information should it deem useful for future time steps. Hence, LSTM was chosen as it solves the problem of vanishing gradients. The performance matrix that was selected for sentiment analysis were classification accuracy and F1 score. Classification accuracy refers to the percentage of correctly classified data, whereas F1 score measures the precision and recall, which measures the ratio of true positives to the total number of labeled positives, and the ratio of true positives to the total number of actual positives. In general, the higher the classification accuracy and the F1 score, the better the performance of the model. Now, I will be explaining how I pre-process my data from stock tweets to convert them as inputs into my sentiment analysis model. There are 5 major points that I would like to highlight in this process, namely, obtaining data from stock tweets, removing undesired data, constructing word-to-index dictionary, removing short tweets from the dataset, and keeping the stock words in the dataset. Firstly, I scrape data from the stock tweets API, which allows me to indicate the range of dates that I would like to scrape the tweets from, as well as tweets that only mention specific stocks only. For my training data, I acquired about 2 million data which were dated the 1st of December and before, whereas for my test data, I scraped 100,000 data samples which dated from the 1st December to the 31st of December 2020. Next, since not all samples have bullish or bearish labels, I removed data samples that were not labeled, as I needed the labels to be the target output for my model's training. Furthermore, there was a drastic class imbalance in the remaining dataset, with the ratio of bullish to bearish samples to be 80 to 20. This is not desired, as training my model on such data will result in a very biased model. That is, if my model only classifies each data as bullish, it would still have a 80% accuracy. This is not good. Hence, I randomly drop samples that were labeled bullish until there is an equal ratio between bullish and bearish samples. After this set, the resulting training dataset size was reduced to 700,000 samples. After that, I performed the standard natural language processing processes to the dataset, which includes tokenization, filtering, normalization, and lemmatization. This converts the raw text bodies of the tweets to the list of tokens. And with these tokens, I constructed a word-to-index dictionary by encoding each unique word to an integer, such that there is a mapping for each word to its respective index. To account for unseen words in the test dataset, I included the out of vocabulary, a OOV token, to include these OOV tokens in the training dataset. I selected words that only appeared once in the entire training dataset. These words account for 1.18% of the dictionary size, which is an appropriate amount. Last but not least, I encoded the target labels as binary numbers, 0 or 1, as the output of the sentiment analysis model is to output the tweet as bullish or bearish. Moving on, I chose to remove samples with 5 tokens or lesser. This is because when the model sees such short tweets, it may think that the word in these tweets hold a large significance to the target label, which is undesired as it may not necessarily be the case. To justify this process, I trained my final model on 2 different training datasets, one without removing these short tweets and one with the removal of these short tweets. As you can see, the performance on the left model is much poorer than that of the right, with the accuracy and F1 score of the left model to be 0.807 and 0.750 respectively, while the right model had an accuracy of 0.879 and the F1 score of 0.811. Last but not least, I also chose to keep the stop words in the dataset. Usually, in standard natural language processing, one would remove stop words in the dataset as they do not hold much information or significance. Examples of stop words include the, to, etc. However, when performing an experiment to compare the performance of models that were trained on data with and without stop words, we can see that by keeping the stop words in the dataset, the model performed better, achieving a higher accuracy and F1 score. One possible reason to this observation could be that trendy lingos with bullish sentiment contain stop words. For example, people often say "to the moon," referring to stocks that they think are going to continue to rise. By keeping 2/3 of the phrase, the model is able to better detect tweets with bullish sentiment. This concludes my data pre-processing step, and now I'll be explaining how I built my LSTM model to perform sentiment analysis. Firstly, the input, which is the list of tokens, will be passed into an embedding layer to convert the words to word embeddings. which are basically vector representations of the word. This allows the model to learn more important meanings and connections between the words, as compared to simpler word embeddings such as a one-hot vector. The embeddings are then passed into two LSTM layers, followed by a dropout layer to regularize the model and prevent overfitting. Last but not least, the output of the dropout layer is passed into the final output layer to output the predicted sentiment, that is either bullish or bearish. While training the LSTM model, I perform hyperparameter tuning to find the best values for the model to produce the best performing model. The hyperparameters that I tuned were the size of embedding layer, the size of LSTM layers, the dropout rate, and the learning rate. I also explored different optimizers for the model to see if some optimizers were better than the others. The optimizers that I experimented with were Adam, Ada Delta, Ada Grad, and SGD. After the experimentation, I found out that the best optimizer for the model was the Adam optimizer. Moreover, while training my model and plotting the training and validation losses, I noticed that the models often converge early. Here are two examples of the loss graph that I plotted. As you can see, the loss converged at the fourth epoch, which is very early compared to the usual model training. To overcome this problem, I attempted to use k-fold cross validation. While it did not help with my problem of early convergence, it actually produced the best performing model with an average test accuracy of 87.9% and an F1 score of 0.812. After tuning the best sentiment analysis model, I compared my model with models that were available off the shelf. The sentiment analysis tool that I chose was Monkey-Learn, and it is a tool that classifies text to be positive, neutral, or negative. To contextualize the output of the tool to my problem, I treated positive as a bullish sentiment and negative to be a bearish sentiment. After comparing their performances, Monkey-Learn actually performed poorer than my model, as you can see from its average accuracy and F1 score compared to mine. Hence, I decided to use my sentiment analysis model to produce my sentiment feature for my stock prediction model. So that concludes my part about implementing the sentiment analysis model. Now, I'll be discussing how I implemented my stock prediction model. Since the stock historical data can be modeled as time series problem, I will also be using recurrent networks, specifically LSTM over RNN, as my model. As the problem is a linear regression problem, I use root mean square error as my performance matrix to calculate my model's loss during training and prediction. Firstly, I obtained stock data from Yahoo Finance, which contains 6 features, namely open, high, low, close, adjacent close, and volume. I grouped the data as a 60-day sequences for the model's input. Moreover, I normalized the stock prices using a min-max scaler to scale the prices to a range of 0 to 1. I fitted the scaler based on the training data only and used the same scaler to scale the test data, instead of just fitting the scaler on the entire dataset. This is to prevent test data pollution. Now, I'll be sharing my journey of how I trained the LSTM model for stock prediction. Firstly, I compared the performance of the model trained on one feature only, that is the close price, versus training on all 6 features. As seen from the diagram below, the orange line shows the actual stock price, while the green line shows the predicted close price. There is a large disparity between the actual and predicted stock price on the left diagram, indicating that the model that was trained on one feature only performed poorer. Hence, I decided to train the model on all features moving forward. And despite that, the model's loss was still very high. I hypothesized that the model's poor performance was due to insufficient training data. The original train test split on the test dataset was a 80-20 ratio, and as you can see from the diagram on the left, most of the spikes resided in the test dataset, which is the green line. Hence, I changed the ratio of the train test data split to 90 to 10% instead. The diagram on the right shows the new split, and as you can see, some of the spikes are now part of the training dataset. Furthermore, I performed hyperparameter tuning to produce the best performing model. The hyperparameters that were tuned include the size of LSTM layers and the dropout rates. The diagram below shows the resultant prediction by the model. And as you can see, the model performed much better and managed to follow the general trend of the price, with a RMSE of approximately 500. In hopes of improving the model even further, I tried to incorporate even more training data for the model to train on. Hence, I searched for stock data that had similar patterns to that of Tesla's. And after researching, the stocks that I chose were Netflix, Tencent, and Nvidia. The diagram below shows their stock patterns, but unfortunately, despite increasing the training data size, the model did not improve. So that's all for training the model on technical features only. This section now shows how I incorporated sentiment feature and using the combined features to train the model. To obtain the sentiment feature, I retrieved all tweets about Tesla for the day and passed them into the sentiment analysis model. I summed up all the sentiment values that was output by the model and calculated the mean value. I used the LSTM model that was tuned previously and trained it on the newly combined dataset. The performance of the model did improve, and as the RMSE of the model decreased from 536.79 to 217.58. Similarly, I tried to increase the training dataset by changing the train test split ratio from 80 to 20 to 90 to 10. However, the performance of the model actually became poorer with a higher RMSE of 292.35. That concludes the section about implementing the stock prediction model. Now, I'll be providing a summary of the results from my models. Firstly, for the sentiment analysis model, the performance of the model generally improved as more tuning were performed on the model. Firstly, the base model performed the poorest with a classification accuracy of 75.6% and the F1 score of 0.672. After performing hyperparameter tuning, exploring different optimizers, using K-fold cross-validation, removing short tweets, and keeping the stop words in the dataset, I arrived at the highest performing model with the highest classification accuracy of 87.9% and a F1 score of 0.812. Next, for the stock prediction model, the first three RMSE values belong to models that were trained on the technical features only. After increasing the training dataset to 90%, the model had the lowest RMSE of 536.79. And despite attempting to tune the hyperparameters and including other stock data in the training dataset, the RMSE did not improve. However, after including sentiment features in the training dataset, the RMSE of the model decreased significantly, achieving the lowest value among all of 217.58%. And unfortunately, as said previously, increasing the training dataset to 90% did not help. So in conclusion, at the end of my FYP journey, I managed to produce a high-performing sentiment analysis model with a classification accuracy of 87.9% and an F1 score of 0.812. Moreover, my experiments managed to show the usefulness of adding sentiment features in the stock prediction, as the RMSE of the model improved significantly. Moving forward, some of the future works that can be added onto this project includes training the LSTM model on features that were derived from the original 6 features that are obtained from Yahoo Finance. Some examples of derived features include difference, amplitude, and volume change. Additionally, sentiment analysis can also be performed on tweets that mention other stocks or crypto that are related to Tesla. For example, Bitcoin. Since a portion of Tesla's earnings come from investing in Bitcoin, there might be a high correlation between the price of Bitcoin and that of Tesla stocks. Now, we have come to an end of my presentation. I hope that you have enjoyed my FYP journey as much as I did. Thank you for listening.